Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on August 22, 2025, which is about 6 days ago. The striking result is that reinforcement learning fine-tuning largely restores out-of-distribution performance lost during supervised fine-tuning, with recoveries up to about 99% for QN 2.57b and about 85% for Llama 3.211b. The paper is titled, RL is neither a panacea nor a mirage, understanding supervised versus reinforcement learning fine-tuning for LLMs, and the implications for model training are quite significant. It shows that directional rotations in weight space, not singular value changes, drive both the forgetting and the recovery, and that low-rank or shallow interventions can recover much of the lost competence before expensive reinforcement learning. On X, reactions highlight that reinforcement learning restores out-of-distribution performance lost to prolonged supervised fine-tuning by reorienting singular vector directions, while low-rank tweaks help. Engagement shows modest likes, around a dozen. Alright, the previous segment summarized community reactions. Figure 1 shows side-by-side bar charts comparing in-distribution and out-of-distribution accuracy at 3 checkpoints, inter-SFT, SFT, and RL. The left panel for QN 2.57b shows in-distribution accuracy rising with SFT, while out-of-distribution accuracy drops and then rebounds with RL to about the inter-SFT level. The right panel for Llama 3.211b shows the same pattern, which highlights that RL mainly restores what prolonged SFT degraded. So the previous figure highlighted accuracy shifts across stages. Figure 2 shows loss curves during supervised fine-tuning for QN 2.57b on the left and Llama 3.211b on the right. Training and test losses fall quickly and flatten, which signals solid in-distribution fitting, while the out-of-distribution loss plunges early, then steadily climbs as steps increase. That rise captures catastrophic forgetting, because the model specializes on the training style, while drifting away from the out-of-distribution regime. Okay, the previous figure tracked loss dynamics over steps. Figure 3 shows singular value spectra for the Q projection, K projection, and V projection matrices, comparing before and after supervised fine-tuning on the top row and before and after reinforcement learning on the bottom row. The colored curves barely shift, while the gray delta stays near zero, which means magnitudes remain almost unchanged. That stability supports the claim that performance changes come from direction rotations, rather than singular value growth. The panels collectively reinforce that both stages leave the bulk spectrum intact. Well, Figure 7 drills into causality. Figure 7 shows out-of-distribution accuracy for two models at the reinforcement learning fine-tune stage, and after applying UV recovery that restores supervised fine-tuning learned directions. The blue Quen curve stays near 20% and barely drops, while the orange Llama curve falls sharply from roughly 16 to about 11. The decline indicates that forcing supervised fine-tuning directions onto the reinforcement learning model erodes the regained generalization, which supports the claim that reinforcement learning helps by reorienting directions rather than by changing magnitudes. Alright, the previous figure established that spectra stayed stable while directions mattered. Figure 6 shows how restoring only the top K singular directions affects accuracy for QN 2.57b and Llama 3.211b. The left panel reports in-distribution accuracy dropping steadily as more ranks are restored, which implies these directions trade off with fitting the training style. The right panel shows out-of-distribution accuracy rising with modest K and then stabilizing, so a relatively small top slice recovers generalization without touching the full spectrum. So the previous figure showed rank-based recovery effects. Figure 5 presents two panels that trace what happens when the top K layers' singular directions are restored. The left panel shows in-distribution accuracy dropping steadily for both models as more layers are restored, which signals a trade-off against training fit. The right panel shows out-of-distribution accuracy staying flat for QN, while Llama first dips then rebounds after roughly 35 layers, so selective restoration can recover generalization without fully sacrificing in-distribution performance. So the previous figure explored layer-wise restoration effects. Figure 4 presents a minimal code demo that estimates and applies a pro-Christie's rotation to align two weight matrices, which illustrates how direction changes can be measured and undone. The snippet computes a true 2x2 rotation, recovers it via singular value decomposition, then aligns weights and checks output differences, so the behavior isolates directional drift rather than singular value scaling. This demonstration clarifies why reorienting singular vectors restores function while leaving magnitudes nearly intact. Wrapping up, 2 takeaways stand out. Reinforcement learning mainly restores out-of-distribution skill that prolonged supervised fine-tuning erodes, and the restoration comes from reorienting singular vector directions rather than changing singular value magnitudes. Practically, low-rank or shallow direction resets recover much of the gain, saving costly reinforcement learning. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.